Hello, everyone. We are Team 20. Our presentation topic today will be about semi-supervised semantic segmentation with cross-consistency training. Now, I'll first off introduce our problem statement. There are two important keywords here which are worth to discuss. One is the method of semi-supervised learning, and two is the semantic segmentation task. So firstly, what is semi-supervised vision? It is the method in machine learning and a subcategory of weak supervision that combines during training a small amount of labeled data and a large amount of unlabeled data. Secondly, semantic segmentation is a task of partitioning an image into multiple image segments or regions. It reduces the image complexity to make further processing or analysis. Since the label data is expensive to annotate, the need for a data-efficient segmentation method is even more evident. As a result, a growing attention in semi-supervised learning to take advantage of large amount of unlabeled data and limit the need for label examples. Here, our topic of research is about proposed idea of using a cross-consistency training method for semi-supervised segmentation. Through this work, we aim to achieve a high accuracy of our segmentation model and enforce the model's robustness against domain shift.
Now I will talk about the difficulties and challenges that semantic segmentation tasks face in the recent progress. With the wide adoption of deep supervised learning within the computer vision community, significant changes were made across various visual tasks, yielding impressive results. However, training deep learning models requires a large amount of labeled data, which acquisition is often costly and time-consuming. In semantic segmentation, given how expensive and laborious the acquisition of the pixel-level labels is, with a cost of that is 15 or 60 times larger than that of region-based and image-based labels, respectively, the need for data-efficient semantic segmentation methods is much more evident. As a result, a growing attention on deep semi-supervised learning to take an advantage of a large amount of unlabeled data and limit the need for labeled examples. However, the recent progress in semi-supervised learning was confined to only classification tasks, and its applications in semantic segmentation is very limited. Dominant approach focus on weakly supervised learning, which principle is to generate pseudo-pixel level labels by leveraging the weak labels together with the limited strongly labeled examples. Generative adversarial networks, GNAs, were also adapted for semi-supervised setting by extending the generic GNA framework to pixel-level predictions. Nevertheless, this approach suffers from some limitations. Weakly supervised approaches require weakly labeled examples along with the pixel level labels. Hence, they don't exploit the unlabeled data to extract additional training signal. Methods based on adversarial training exploit the unlabeled data, but can be harder to train.
I'll be going over the related work. Recently, many efforts have been made to adapt classical semi-supervised learning methods to deep learning in order to overcome some of the weaknesses mentioned. In our work, we focus mainly on consistency training. Consistency training methods are based on the assumption that if a realistic form of perturbation was applied to the unlabeled examples, the prediction should not change significantly. Some other related works in semi-supervised learning include the pi model, which enforces a consistency over the two perturbed versions of the inputs under different data augmentations and dropout. Instead of relying on random perturbations, virtual adversarial training approximates the perturbations that will alter the model's predictions the most. Similarly, the proposed method enforces a consistency of predictions between the main decoder and the auxiliary decoders over different perturbations that are applied to the encoder's outputs rather than the inputs. Our work is also loosely related to the multi-view learning and cross-view training, where each input to the auxiliary decoders can be viewed as an alternate but corrupt representation of the unlabeled examples. Next slide. Recently, CalMix, a concurrent method, was introduced. CalMix uses mix-up, which enforces a consistency between the mixed outputs and the predictions. But cross-consistency training differs from CalMix. Number one, as traditional consistency regularization methods, CalMix applies the perturbation to the inputs, but uses mix-up as a high-dimensional perturbation to overcome the absence of the cluster assumption. Two, CalMix requires multiple forward passes through the network for one training iteration. And three, adapting CalMix to other settings may require significant changes, but cross-consistency training is efficient and can be easily generalized to other settings.
Next, I will talk about the data set we use for our replication. There are three settings in the replication and each use another data set. And first one is a semi-supervised testing that we will use Pascal VOC with augmented training set. And second one is a partially overlapping label spaces. This is a domain application of the semantic segmentation, and we use cityscapes and Canvas. And for non-overlapping label spaces, we use cityscapes and sun RGBD. And the data statistic is shown on the right here. We have number training, validation, and testing image, as well as the number of classes in each image.
Now I'll present the solution and our potential improvement. Before to start with, I want to talk about the important encoder-decoder architecture. So as you can see on the slide, the encoder-decoder architecture is widely used in the image segmentation test. Basically, the principle is that when we feed an input image into the network, the encoder would then compress the input into a feature representation, which contains the underlying semantic information of the input image. After that, the decoder would take this compressed representation, extract information from it, and produce the output segmentation map for our input image. So now let's take a look at the paper's method. For our specific problem, the solution is cross-consistency training, CCT for short. Let's take a look at the overall recipes for our method. To your right is the whole paper's encoder-decoder architecture that I would go into details later. Firstly, for training dataset, we have a small pixel level label dataset and a large unlabeled set. In addition, we might have another set of image level label training data. Secondary, regarding the model, we have one shared encoder, one main decoder, and several auxiliary decoders. Each auxiliary decoder contains a perturbation function. Our main goal of the method is to enforce a consistency in the module's prediction over several small perturbations of the input images. So our training scheme involves several different phases. The first phase is supervised learning with label training samples. You can see the overall process here in the diagram. So basically, we'll feed the input image through into our network and compute the supervised loss based on a new version of Bootstrap cross entropy loss, ABCE for short. ABCE is pretty similar to the cross entropy loss that we have been using in our class, with the only difference is that in ABCE, we only compute the supervised loss over the pixels with a probability less than the threshold. These thresholds gradually increase over the training time. The next phase is dealing with unlabeled data. You can see the overall process here again on the diagram. Basically, in this phase, the feature representation from the encoder is fed into the main decoder and all of our auxiliary decoders. In the diagram, I only show one auxiliary decoder for simplicity, but in reality, all of them are used. Finally, we produce pairwise mean square errors between the prediction of the main decoder and the prediction of each auxiliary decoder. We sum them up and then produce our unsupervised loss. The next step is optional but extremely useful, which is weekly supervised learning. We have this optional step because sometimes, apart from label and unlabeled data, we are also provided with image level label data, which is a crucial source to generate more pixel level label training data. So for this phase, a lot of inspiration is taken from the famous class activation mapping method. Basically, we would pre-train the share encoder with an additional global average pooling layer and classification layer on the image classification task. After that, we would use this pre-trained share encoder to generate the class activation maps from which we could obtain the pseudo pixel level label for the input image. So basically, we generated more labels for supervised learning, but these newly generated labels are much more unreliable compared to the given pixel level labels. Finally, we plug the pre-trained share encoder into our network and train the network and produce the weekly supervised loss. Next slide, please. So for domain adaptation, the intuition behind this idea is to train our network using datasets from different domains. To put it simple, doing this, we can push our model toward better generalization at inference time. Next slide, please. So finally, based on the presented phases, we have our combined loss for cross-consistency training here. It is the sum of supervised loss, weighted unsupervised loss, and weighted weekly supervised loss.
Regarding the improvement in comparison to the paper, first one, we can change the backbone for the share encoder with the SOTA architecture. According to a famous notebook for cargo grandmaster, Jeremy Hogwarts, the classification accuracy and the inference time of each model are shown in the image here. And it can be seen that the BEIT model family yields the highest classification accuracy on the ImageNet, and also VIT and ConvNext in Tutu also obtain a great performance with less training time. Second one, we can modify the objective function in the paper. We can see from the paper that it is only perturbation on the learned feature from the encoder and CAM model to create semi and self-supervised architecture. So one simple idea here is to utilizing a file transformation like rotation, flip, and random crop to create a new self-supervised term. We get this idea from the borrowed tree methods of the Facebook research.
So one final proposed improvement that our group is thinking about is to tweak the architecture of the current paper's model. So the idea is that as we see, the way we see it, the current architecture of the paper's model take a lot of inspiration from the P model. So while it is somewhat a good solution, we feel that using temporal ensembling could be a good idea to achieve better results. So the advantage of temporal ensembling compared to the P model is that unlike the P model, the outputs of multiple previous network evaluation in temporal ensembling are aggregated into an ensemble output, and it is used for the unsupervised learning process in the current training iteration. As a result, it could reduce the noise in our training data. Next, the feature representation is evaluated once only in the main decoder. In the P model, we evaluate the feature representation several times through the main decoder and a lot of auxiliary decoders. So this means that temporal ensembling could us to achieve a speed up over the current model of the paper. So this leads to another advantage of the temporal ensembling is that we can have the possible elimination of auxiliary decoders. This means that we can reduce the complication of our network as well as the number of learnable parameters. So here are the reference that our group used to make our presentation. So that's it for our presentation.